In today's operating system lecture, we are going to be looking at input-output. Um, when we were looking at the various things about operating systems, we have always referred to input-output devices and how information can come in and go out from these input-output devices. That's what we are going to be focusing on today, and we will not be particularly looking at the devices today. That will be in the upcoming lecture, but today we will be mainly looking at the the input-output controllers and the main common components relevant to input-output management within an operating system. So, as with anything within a computer, the operating system is also going to be responsible for managing and managing any sort of input-output devices that are attached to that particular computer. So this can include storage devices, keyboard, or like any input devices like that, printers and displays type output devices, network interfaces, communication devices. So any variety of input output devices, and all of them will have to be managed by the operating system, or a part of the operating system will be responsible for managing these input output devices. And the operating system plays a number of roles when it comes to input output devices. So the operating system will act as an interface between the devices and the rest of the system. So the operating system will be in the middle, and on one side it will be the devices, and any other software or any other system will be able to access these devices through the interfaces provided by the operating system. So operating system will be that intermediary component, and by doing that, operating systems can give a what is called a unified interface or device independent interface to these other systems. So for example, even if we have a number of variety of printers that can be attached to a computer, the operating system may give a singular interface about printers through which any program, any process can access printers. And in addition to that, operating system will be responsible for issuing any sort of commands into these devices and possibly managing interrupts. So interrupts will come when a task is completed at a device. So then managing those things, and also possibly managing or handling errors. So if input-output device is tasked to do something, and if it encounters an error, then it will be the responsibility of the operating system to manage that situation. And one of the main reasons why input-output needs to be in operating systems is, unless they are implemented at the operating system level, what we will have to do is each and every program, each and every process will have to manage its own input-output capabilities, and that would be much more complicated. So whereas a single operating system can know about every sort of different input-output devices, same level of understanding, bringing that to each program or each process will make those processes much more complicated and complex. So this is in a way delegating those responsibilities to the operating system. So the operating system will take responsibility for managing these devices, and the processes and programs can directly talk to the operating system and not bother about the underlying devices there. So when it comes to input-output devices, we can divide them into two main categories. Not all the input output devices may not fall into these categories exactly, but these would be sort of covering most of the input output devices into one of these categories. So the first one is what we call as block devices, and the second one is what we call as character devices. So the main property about block devices is they um, they access or they handle data, handle information coming in and going out of these devices as blocks of data. So they may receive blocks of data that can have a number of like differing length of data, but they will be received as these blocks. So a good example of this is when we consider a storage device like a hard disk, where it would store information in these units of blocks. And all the actions or the reading or writing or any access related actions will be performed on the whole block itself, not at individual bytes or bits per se. It will be the whole block itself. On the other hand, we can have certain other devices that may transfer information as characters. Again, a good example for that could be a keyboard, where once you press a key, it will just send that key press information as a character. Then when another key is pressed, it may send that key. So these two types of devices we may find in sort of different combinations. So we may find in block type devices mostly in storage devices, whereas we may find in character type devices in keyboards or communication type devices may fall into that category. And when we consider different types of devices, we can see a large variation in among these devices, even with same category of devices or across different category of devices. There could be a large number of different standards or different types of these devices, and for all these different types of devices we would again have a variety of speeds, for example. So what we would see is these devices are going to be significantly different from one another. So the implication from that is the operating system will have to have some ability to manage these differences. Say, for example, if it is copying something from one type of a device onto another type of a device, say it is copying a file from a CD-ROM onto a hard drive. Now, these two devices may have two different speeds. Say, the reading speed of a CD-ROM and the writing speed of a hard drive may be significantly different. So now the operating system will have to manage that information flow in a manner considering the speed differences there. So this is also one of the things the operating system will have to do, that is to manage the variety of devices that can be there and managing sort of any issues related to interoperability between these devices. Then when we think about most input output devices, they are going to be consisting of two sort of major components. One mechanical or core component, mechanical or even it could be electronic component depending on the type of the device, which is the core component of the device. So if it is a printer, the printer head and all those assemblies would be the main component there. If it is the camera, it is the sensor and the lens and all these things are the main component of that device. So that is the device part of the I/O device. Then these I/O devices will also have some electronic components that are managing these devices. So if it is a printer, there needs to be some logic built into that device that will say when to release ink, or when to move the heads and how to move the heads, when to intake paper and so on. So those things would be managed by what is called the device controllers. So these device controllers are what we would or the operating system would try to interface with. So what we would expect is the operating system will expect these device controllers to be connected through certain standard interfaces. So sort of common interfaces, such as if you think about a storage device, you may connect it through a SATA or SATA port or interface. So such sort of standards will help operating systems only to communicate with these standard interfaces, and then the device controllers will do the underlying logic or lower level operations within those devices. So for example, if we are writing a file onto a hard disk, the operating system will transfer that information onto the device controller and may give some instructions, but then the device controller will be responsible for spinning the disks or moving the arm or header arm and so on, will be the responsibility of the device controller. So that is the one that will do the low level operations for that particular hardware. So now let's look at some of the things, some of the activities an operating system will have to do when dealing with input-output devices. So if you sort of rewind back to when we were discussing processes and process states, there was a discussion about processes going from running state into block state when they need to do some input output activity. So when they were waiting for input output to complete, they went into the blocked state. Then we said when they need to come out of that block state, the device will have to issue some interrupt to indicate that particular task is now completed. So that indication, the activity of indicating to the CPU to say that IO task that was given is now completed, is what we call as an interrupt. So it is a way of signaling the CPU to say the task that was given is now completed. So what we would have is, instead of all these devices directly sending those interrupts onto the CPU and overloading the CPU, what we may do is we may have an additional component that we call as the interrupt controller, and this interrupt controller will be able to manage those activities with the devices. So all the external communications with the devices will be managed by the interrupt controller. So interrupt controller will manage all these communications, but then at the end it will only issue interrupts when needed. So that is what we mean by interrupt. So interrupt is basically a signal that will inform the CPU to say, okay, whatever the given task for that particular IO device is now completed. And then when it comes to interrupts, again we can identify, or we would identify what is called as a precise interrupt as the type of interrupts that we would prefer to have. So again, when we think about this situation of say situation about process states, and processes are moving from running, ready and stopped states, blocked state. So a precise interrupt is when it stopped at a point where every code or every instruction before that is executed. So every instruction before that is executed, and every instruction after that is not executed. So if that is the case, what we can do is we can say stop at this point. These are all executed already. So when we come back again to that process, we can go with these. Whereas if we have a situation where we stop here, but some of these are also not completed and some of these have already started. So if that is the case, then it would be very difficult to restore back to that process. So that is one of the reasons why we would want to have precise interrupts where all the instructions before the program counter or the current instructions are fully executed, and all the instructions after that are not at all executed yet. And when these when interrupts does not meet these requirements or follow these criteria, then we would call them as imprecise interrupts. And the main reason being when the situation is like that, when they stop somewhere middle like this, we would not have much information about what is happening before and after those interrupts, and it may not be ideal to switch back to that process. So then when we think about input output devices, now we can think about how the operating system is going to communicate with these devices. So the operating system needs to transfer information to these devices. So it needs to have a way of identifying these devices and sending information. So to do that, one of the approaches we can take is what is called memory mapped I/O. So here what we would have is we can have, say, the address space, so like the input output devices or whatever the storage related to information that may be needed to communicate with the input output devices. They may be we may use the memory addresses or the standard memory addresses and communicate with them as we would with any other memory device. So the storage or the input output devices and the main memory or the main sort of memory locations will be all sort of accessed similarly. We can have two different approaches here, that is having different memory allocations for I/O devices and the main memory, but regardless what we would have is the operating system or the CPU can just communicate with these devices by writing at that memory locations. So what we would end up with when we do this type of a memory access is we would communicate with input output devices and memory devices in the same manner. So we are going to use the same instructions to read and write from memory devices as well as input output devices. The disadvantage with this approach is it will impact the performance of the memory, because part of the time that particular communication bus is going to be used by other input output activities. So to manage that, what we would do is we would have a additional memory bus that is connecting only the CPU and memory, and any information traveling between the CPU and memory will be communicated like that, and input output devices may communicate through the common bus. Then another approach that we have with memory access or like accessing input output devices is what is called direct memory access. So here again we use this direct memory access for a number of reasons. So one is when a CPU needs to say access a particular device, CPU can give the control of communicating with that device to the DMA controller, and then DMA controller will do all the necessary access management or communication with the device, and then only interrupt the CPU when something is needed. So the DMA controller will be a special purpose process that will normally do this, and it's what we expect from it is uh, to manage all the input output related activities such as communicating with the devices, communicating with the main memory if information needed to be moved from the device to memory. All these tasks will be managed by the DMA controller, and at the end they will interrupt back the CPU to say whatever the IO task that they were doing is completed. So now when we think about input-output software uh, in an operating system, we would expect certain things to happen with them. We would have certain goals for these softwares to meet. So one is we would expect them to be device independent. So for example, if we consider writing a file, we would expect writing a file from an operating system to be the same experience when we write to a hard disk or a solid state drive or an external drive. So all these different categories of devices could still be accessed or communicated through a device independent interface. So that is something that we would prefer. Then across sort of different types of devices, from an internal point of view, when they are internally represented, we would prefer to have some uniform naming conventions. So this is again to make it easier for us to identify sort of the differences and commonalities across these devices. And we would also expect these devices to do error handling. Say for example, if a file is being written onto a hard drive and it finds a bad sector and no information can be stored there, so it has to skip to the next sector and so on. So this type of an activity, and then when it encounters an error, we may have to the operating system IO software component will have to manage that error effectively. So that is what we would expect from a error handler. There's a question about is the DMA controller inside the CPU? No, so the DMA controller would be a special purpose processor that would normally be outside the CPU, but normally in the same motherboard, for example, and it would be particularly tasked with communicating with input output devices and transferring data across between devices and main memory. So what it helps is, say if a DMA controller is not there, then the data transfer happening from here to here will have to be happening in the observation of the CPU. And so it may waste a number of CPU cycles to do these additional transfers and so on. So by having a DMA controller in the mix, it can do all these activities, so it can manage all these things because it is a processor on its own, so it can do its own processing, doesn't have to rely on the CPU to do basic computation. So it will do some basic computation to relevant to this transferring of data, and then only inform the CPU when that task is completed. Then again, coming back to input-output software, we may want this input-output software to support a few different ways of transfers. So we may sometimes want what is called a synchronous or blocking type transfers, or sometimes asynchronous or interrupt-driven type transfers. So in blocking type transfers, what would happen is it basically blocks. So until, say, if it is say, for example, reading something, it will stop the program until that task is completed. So it will stop the program, go into the read action and come back. Whereas in asynchronous transfer, what we would have is it would let the transfer happen until some until some interrupts occur. So it will let it go as long as it needs to go until an interrupt is encountered. So that is again a few different types of transfers that we may encounter. Then one of the most important things that we would expect from I/O software would be buffering. So why we would need buffering is different devices may run at different speeds. So when we have devices running at different speeds, we would need some intermediary place that can, say, accept data at a much faster rate, but then only transfer forward at a much lower rate. So we may have to have some buffering capabilities for us to sort of manage or cater to sort of a variety of devices. And then one of the other things that we may expect is when we have a number of processes that may need to use the same device, we may expect the operating system to make those devices shareable, but certain devices we may want them to be dedicatedly used by a particular process. So in that case, we may want the operating system to designate those as dedicated to a particular process. So that type of control may something that we may need depending on the circumstances. Say, for example, if it is a printer can only be assigned to a single process until a particular print is completed. When it is transferring that information and so on, it should be allocated as a dedicated device. So now, when we think about input-output devices and how input-output communication or transfers can happen within an operating system environment, we can sort of categorize them into three sort of main methods. One is called programmed I/O, the second one is interrupt-driven I/O, and third one is input-output using direct memory access. So with programmed I/O, what we have is the CPU is the one that is doing all the input-output related activities. So all the input-output related communication will be manually or individually managed by the CPU. So the CPU will, say, for example, if it needs to transfer these characters or text to a printer, the CPU will take that information and send one by one into the printer. So then it has to wait until the whole task is completed, because even though it is only doing that input-output task, while the CPU is doing these input-output related communication tasks, it cannot do any other computational task. So what we may end up with in a situation where CPU has much more important things to do, so we wouldn't want it to be wasting its time in doing this input-output related communication. But this is a very basic and simplest form of input-output. Everything is managed by the software component of the operating system. Then the second type of input output is what we discussed previously about interrupts. So by using those interrupts, we can again do um, input output communication. But the main difference here is now the CPU can give the instruction to the interrupt controller, and then let the interrupt controller manage these tasks and only get the information back at the end. But the problem here is, or the difference here, or the disadvantage here is, so the advantage is CPU can delegate this task and go to execute other instructions or other processes. But what we may get is this interrupt controller might interrupt the CPU too often. So if the interrupt controller is coming back to the CPU and interrupting it a lot of the time, that could also be a problem, because say for every input output task, and if the interrupt controller is coming back to the CPU and disturbing it, that may not be something we would prefer, because it may waste the total execution time or total time available for actual computation. Then the approach with DMA controllers is also fairly similar to what we may do with interrupt controllers, but the main difference being in interrupt controller will mainly manage the communication with the devices, but it will not manage the data transfer with the devices directly. It will mainly manage whenever it is almost like, instead of every one of these things interrupting directly, this is like a collection point for interrupts, and that will send those interrupts onwards to the CPU. So the CPU doesn't have to wait and listen to interrupts. But on the other hand, using DMA, here it's not just managing the interrupts, it's almost managing all the data transfer tasks. So here the CPU will delegate the actual input output tasks to the DMA controller, and then DMA controller will go and do all the necessary steps and execute all the necessary instructions to do the IO task, and then only interrupt back the CPU when all of these things are completed. So comparatively, DMA controllers will be much more advantageous than just using interrupt controllers. But with DMA controllers, one of the main disadvantages we may have is because of the speed difference. Because we already said DMA controllers are going to be special purpose processors. So with those special purpose processors, what we may expect them to do is communicate with the CPU. But if the CPU is much faster and DMA controllers are much slower, because we may not ideally use the same sort of faster processor for both, so most likely DMA controllers will be much slower processors, and that may affect the total processing when there are no other processes are waiting. So say if 8 processes are waiting to be processed, then handing in the control to the DMA controller is a good thing, because CPU is not going to be disturbed that many times. But if there's no other devices waiting for IO, then in that case DMA controllers may not be that ideal of a solution. So then within the operating system software, and with sort of as the whole software layer, we can categorize, or we can identify the input output related software at sort of as in a layered architecture. So what we would have is, we would have the hardware layer at the bottom. So the hardwares will, whatever the input output hardware will be there. Then at the operating system level, we would have the interrupt handler component. So the interrupt handler component is the one that will be at the lowest level because it has to interact with the hardware directly. So any sort of signals from the hardware will reach the interrupt handler. So then beyond that, we would have what are device drivers. So these are device specific software components that will coexist with the operating system components. Then above that, what we would have is the device independent operating system software. So then operating system will also have the device independent software layer, which is what normally used by the user software. So whatever the user level IO software, that will communicate with the device independent operating system layer to do any sort of interaction with the input output devices. So the starting from the bottom, hardware layer is the hardware layer. So the next one is the interrupt handlers, and interrupt handlers, they are like a unavoidable thing in input output, but they are also not so great because they can hinder the performance of the CPU. So we have to manage them considerably. And because like whenever every interrupt comes in, CPU will have to stop whatever things that it is doing and go into the interrupt and look at that and do certain things. So having interrupts like that, and then that particular interrupt cycle may take a number of CPU instructions. So that is one of the reasons why we would want to avoid input out interrupts, but with the input output devices it may not be practical to totally avoid them. So when we think about interrupt handlers, they will go through this set of steps when they are encountering, or when they are issuing an interrupt, or when they are encountering an interrupt. So when an interrupt comes, the CPU will have to stop whatever that it is doing and save that information somewhere. So it's like the context switching that for that process. So then it has to also identify what is called the interrupt service procedure. So that is the set of instructions that have to be executed when an interrupt occurs. So that interrupt service procedure will be the next thing to look at. Then like we may go through a number of stages, such as say acknowledging the interrupts, and then copying whatever the relevant information back and forth, and then like going through that particular procedure and whatever that it dictates, and then at the end going back to the previous process or start a new process. So that is sort of the basic stages of interrupt handlers. But in sort of reality, this is not something that you would be tested in terms of all the steps of interrupt handlers and so on, but that is something that you need to know. Then we can also have, beyond that, what are called the device drivers. So device drivers are piece of software that would coexist at the operating system space, but are specific to a particular software. So you may come across device drivers for printers or any sort of various devices, and the reason being, even though these devices will have will follow, say, certain standard interfaces and so on, they would still have certain internal differences. So different companies may manufacture these devices differently. So then there will be some internal details very different from one printer to the another. So it may not be practical to use a single device independent software. So just leaving that layer as it is, and then we will have what is called these device drivers, and they are again additional pieces of software or libraries that can give the particular instruction for that particular type of device. So like say different interfaces to control these devices, change parameters in these devices and so on can be provided using these device drivers. And device drivers would also be responsible for managing sort of the specific communication patterns, power management, and so on for a particular device, because different devices may have different ways that they need to be instructed. So those differences, those communication patterns, and so on will be managed by the device drivers. In certain operating system environments, there may be certain common device drivers that may already be available, and there may also be certain types of devices that may follow sort of standard device drivers, so they may not be needed to be installed separately. So, so that is what we would expect from a device driver to do. So there's another question there about interrupts. So there are two things. One is interrupt handling, and the other one is interrupt controller. So interrupt handling is when an interrupt is received. So say when we have an input output device, so we have a IO device, and that IO device may need to communicate with the CPU. So when it sends an interrupt, the CPU will have to manage that, and the operating system will have those components. So that operating system component is what we would identify as the interrupt handler. Then we can also have an additional hardware component in between this to manage this signaling between the CPU and the input output devices, and that is what we would identify as the interrupt controller. So the interrupt controller is a hardware component, and interrupt handler is a operating system software component. Then above the device drivers layer, we would have the device independent operating system software, so input output software. So these are the ones that would provide a uniform interface to all the other software and other processes that may need to access these devices. So from the user level software, this device independent software will have a unified interface for a particular type of device. So all the keyboards may have a particular type of interface, all the pointing devices, web cameras and so on. So for each category of devices, they may give a standard interface through which various functions can be communicated. Then underlyingly, they may communicate differently through the device drivers. So what we expect as this uniform interfacing is like say if we have like a number of storage devices, number of possible storage devices, or sort of standards or connectivity possibilities to connect to storage devices. So what we could expect to have is sort of either few different interfaces. So when we say different system calls or different instructions to be issued and different ways of receiving those signals, so it could be that, or operating system can only provide a single interface to all the device drivers. So operating system doesn't have to implement many different ways to connecting to those. It can only provide a single way to connect to all the devices, and all the device manufacturers will create device drivers to that particular interface. So this part, the drivers will be manufactured by the device manufacturers along with the device. So they will know, okay, to work in this operating system, they will have to create this piece of software to match with this particular interface. So that is what we would expect to have with these device drivers. Then another thing that, as we said, depending on the type of process or type of devices that we may use, we may have to have some form of buffering. So if like either we can directly communicate to a processor, to a device, for example, but if the speed differences are there in terms of how fast it can receive and so on, what we may do is we may buffer it somewhere, either in the user space or in the kernel space somewhere. We could store that temporarily and then access that later when that is needed. This can be done either in a device to process communication or transfer, or device to another type of device transfer. Again, buffering can be used in those instances as well. Another important thing, as previously mentioned as well, managing errors will be an important task of operating systems, because say for example, when you were trying to write a file onto hard drive, the hard drive becomes full. Now it has to indicate that to you to say that's an issue, you cannot write any more data onto that drive. So it has to manage that. So even in terms of errors, there can be number of things. So there can be sometimes program errors. So you may try to say issue a command that is not acceptable for a particular type of device. Say you cannot ask a printer to scan something, or like if it doesn't have a scanner, or to issue a sound signal through a camera. So if like sort of wrong informations or wrong instructions are given to devices, that is something, a programming error, so that has to be managed. But then it can also have actual errors, say part of the device has failed, a component inside the device has failed. So those type of things will also have to be managed accordingly by the operating system. And one of the other things we would expect the operating systems to do is about allocating and releasing devices. So say when we have these devices across different processes, so different processes can use different devices. So especially some devices are normally expected to be used by a single process. Like a printer, you would expect only a single process to be printing on a printer at a single point in time. So in these type of scenarios, you would expect that control or that management in terms of how they can access these devices will be managed by the operating system. So operating system will allocate a device to a process, and then it may release that from that process and then reallocate that to a different process. And the other thing that we would have, particularly in disk type devices, is what is called a device independent block size. So when we think about block size devices, we may be communicating in the sizes of blocks, but the underlying architecture of the device may have a significantly different block size. Say, for example, you may consider from a programming point of view, you may have a block size of 32 bytes, but whereas the underlying storage medium may have a block size of 64 bytes, or the other way around. So then the operating system will only consider this from the user software point of view, but then when it's communicating with the other side, it may consider the underlying block size of the device as well. So at the higher level of this layered architecture, they may work with the device independent block size, and at the lower layers they may work with the device specific block size. Then at the very top of the layer is where we would have the user I/O software, and user I/O software is basically so any software or any software component so that is relevant to communicating with these I/O devices. So even though we have this device independent software layer, even inside our user space software layer, we may have some libraries, for example, included to do some specific communication related to input output. So things like printing libraries or scanning libraries and so on, we may have some additional capabilities built into the software itself, so it at least knows how to communicate with these device independent software interfaces. So that is something that we would have as part of the user space software also. So then there's another sort of special type of input output software related component that we can identify in operating systems, which we call as spooling systems. So what spooling systems do is they are a way of managing requests from a number of different processes, and these spooling systems will manage the communication with the devices. So say, for example, if we have a number of processes, so these processes all need to print something. So then they may need to communicate to a printer that is somewhere, and there are two ways. So one is the operating system can allocate them one after the other to the printer. So first this one is allocated, then when that finishes, the second one is allocated. When that finishes, the third one can be allocated. So that is one way of going about it in terms of allocating, but that needs to be managed by the operating system. An alternative way of doing this is what we can identify as a spooling spooling process or spooling system, or sometimes we may call it a daemon process. What is it? Is an intermediary process that would receive all the requests from all the processes, and it will keep that in a buffer sort of a thing, and then this one will be the only one having access to the device. So this printing daemon or the spooler will have access to the printer all the time, all the request will be coming into the spooler, and then printing will happen like that. So these individual processes need not to be allocated to the printer directly, and they can print through this common processor, this special process. So that may also be there in certain operating system environments depending on certain input output devices. So, as a summary, what you all need to know about input output devices is they are not just going to be a single layer of operating system component that is going to deal with input output devices. There's going to be a number of layer of different software that is going to deal with these input output devices. So all those together we would identify as the input output subsystem of a operating system. So starting from the libraries in user processes to the underlying hardware components, all those things working together is what we would have in a input output system. So that's all for today on input output devices, and please check LMS for more details about the quiz, and I will post the more particulars there as well. And if there are any concerns and any students with limited access and so on, please ask them to contact me on time. Other than that, that's all for today. Thanks for joining in the lecture. See you next time. Bye.